I'd like to thank Andrew Childs, Stephen Jordan, and Jake Taylor for having me. I guess looking at the program, I'm maybe the only experimentalist to speak. And it's perhaps a provocative title. On the other hand, if we're successful, I think, in any of these platforms that are starting to be built up right now, I think it has to be with deep engagement with your community. And that may be rather obvious, because if this is to be useful, it will be applied to some algorithm that people from your community have developed and so forth on the theory side, computer science and mathematics. But I think it's deeper than that, because I'm learning recently what the topic of co-design means. And even in classical computing, the idea that a computer architecture, especially in the early stages of its development, is tightly bound with the application. We don't see that so much right now in standard classical computing, because memory is so cheap we don't even have to keep track of it anymore. But in quantum computing, this is certainly not the case yet. We don't have devices that are for any, can be put to any use for anything, very, very useful at this point. But on the other hand, I think inviting people from your community to sink down into the laboratory and maybe understand the natural connectivity of experimental systems is important. There are certain natural interactions that are easy to harness, relatively easy to harness, that you should be aware of and take advantage of. The graphs may not look like the ones that you're used to. For instance, a nearest neighbor graph in 2 dimensions might not be the easiest one that's built out. And from my perspective, again, I think it's like going to school again, which makes this field so great, learning what types of algorithms are interesting and what their graphs look like, what types of natural gate structures we should be looking for in the lab. And this holds for algorithms, it holds for error correction, which is sort of a natural modular type structure where you have logical qubits. That's one example. So, maybe provocative, but I'm here to provoke, especially your community. All right, well, so what I'm showing here is sort of a concept picture of it's a very concrete one, what we have in mind. The idea is to build a modular device where each of these red boxes holds a bunch of qubits. In the technology I'm most familiar with, these are individual trapped atoms, atomic ions. And there are local interactions that are almost fully connected within the module. And then at some point, I think if you leave this talk with any message, it's that any physical platform will have to be modular at some level. And in this case, we break out of the modules by having, for instance, a photonic coupling, which can go over long distances. And that might not be necessary in the short run, but in the long run, certainly if you want to appeal to communication applications, you're going to want optical quantum communication. And this other stuff, I'll sort of get to this, the idea of linking together modules. You can sort of already see a graph here that is highly modular, and I want your community to start thinking about the graphs that are sort of natural in the laboratory. Well, it's an interesting time now. In the last few years, many of you know all of the enormous investments, mostly in the US, but also in other places, in starting to build a system. And almost all of this, well, most of these investments are actually in superconducting systems. And so I list here, this is maybe a little controversial, I'm not so sure. I think these two technologies right now are at the stage of being ready to be built up, where engineering should now come to the task, and instead of just doing demonstrations of gates and so forth, actually build something big. So superconductors and trapped atomic ion qubits, they're quite complementary when you consider these two systems. I'll talk almost entirely about this platform. Atomic ions, the nice thing about atomic physics is that the atoms are given to us, they're identical. When left alone, you can make them identical to parts in 10 to the 15. It's not actually all that hard these days. So left alone, atomic qubits are sort of naturally scalable, unlike any solid state platform. So it's an interesting argument to make. Solid state platforms such as superconducting loops, you think of them as scalable because you can buy a bunch of them printed on a board. And that's true, that's a big advantage. Big disadvantage in atomic physics is we don't have that infrastructure. We don't have the engineering yet. So I think maybe for your, one thing this community might be interested in is the natural connectivity and reconfigurability of atomic ions versus most solid state platforms, which are literally wired together with superconducting wires or inductors, or in different platforms, even broadening it in solid state, you can again print these circuit boards and have electrical currents transmit quantum information. The atomic ions, at least in the platform I'll talk about, and I'll spend a little time on this, the connections are not, they're not set up on the board. The qubits themselves don't have connections unless you connect them from the external, from the environment. And we do this with electric fields from lasers or maybe microwaves. But the point here is that the qubits themselves, the graph is not given by a 1D next neighbor connectivity here. It's actually, it can be fully connected. It depends on the power and spectrum of these lasers. So that's done externally. So it's a reconfigurable platform, which is very interesting. That's a huge advantage because in a sense, it makes it much more flexible to apply to different types of problems. So you can sort of see that they are complementary. I think the superconducting circuits right now are enjoying very large investments from industry and also the government. And we're going to see pretty soon how far they can build this system up. I don't include D-Wave here because, again, that's a pretty controversial machine that they've built, and it seems to rely more on thermal effects than quantum effects. But there are legitimate efforts to actually build superconducting quantum computers from the bottom up, in particular the Google USB team led by John Martinez. We've heard of a recent investment at Delft by the government and also Intel. Now, the investment, and it sort of makes sense, the investments in atomic physics has taken some time. It's quite a bit smaller level, and it's because the engineering is not there. So it sort of makes sense to try to see how far we can push this technology. And I'm very interested in what happens here because I think it will impact in 5 or 8 years, what we'll be doing up here. Now, I list a few other technologies that are, there's wonderful research in NV diamond and other color centers in solid state materials, and semiconductor gated dots, other forms of atomic physics systems where you don't have individual control of the atoms, but it's more of a global type, maybe quantum simulator of certain models. And these, at this stage, they're pretty exploratory but incredibly exciting type physical platforms. And I would say that at the Joint Quantum Institute, which is sort of the physics branch of quantum science here at Maryland, we're interested in all comers, all physical systems that can host many body interactions, quantum gates, and condensed matter physics at very simple levels. Okay, so let me now that I've tried to sell you that there are two sort of different visions here, I think these can both be built up simultaneously because I think in the long run they will be applied to different problems. And hopefully in the next few minutes next 20 or 30 minutes, I'll sort of give you a flavor of what that means. Okay, so trapped atomic ions. Well, here's a picture. This will tell you already that there's a lack of engineering. This is a picture of an ion trap from my laboratory that was clearly hand assembled. You can see the screws here. Now, the individual electrodes themselves, and by the way, that horizontal gap, it's a couple of millimeters, so it's not nanoscopic or anything. These electrodes are indeed ceramic with gold that's evaporated on them, but there's not much more lithography than that. You can see that these are wire bonded in our laboratory, and it's in a vacuum chamber and so forth. And in the gap in the middle there, I'm not going to talk too much about the physics of ion traps. It's a pretty well-established field in atomic physics. But in that vacuum gap right in there, we have, in this case, a bunch of individual atomic ions that are confined with electric fields. And these ions can stick around for long periods of time. In one of our traps, we've held a single ytterbium ion for 3 months, the same ion. I think it's the same ion. We come in the next morning and turn the system on, and it's still there. I mean, it's very unlikely that one left and came in spontaneously. Now, there are issues when you pack more ions into a trap. There are issues that we don't exactly understand on lifetime, but we can hold on to 10 to 20 individual atomic ion qubits for hours. That's really not a big deal. I'll maybe comment more on that later. I list here maybe not complete list of the laboratories throughout the world that are investigating trapped ions for quantum information applications. There's maybe 35 or 40 groups actively pursuing this. And I think this is notable because 20 years ago when I started in the field, there was only one that really had the capability and in one group that was really building gates, and that's what Dave Wineland was doing. And I was working with him for almost 10 years in Boulder. And this is great because the field is obviously very young. There are lots of newcomers to this field, and it's still growing enormously. Okay, so there's the system. Let me now dig even further down into the individual atoms. So we're going to imagine qubits, one per atom here. And oh, by the way, I forgot to mention, while we don't lithographically fabricate fancy ion traps, it is being done, and it's been, this is over the last 10 years or so, especially at Sandia National Labs, Georgia Tech Research Institute, and Honeywell. They're making traps etched from silicon. So this trap here, for instance, we need to send laser beams in these traps. And you can sort of see this trap, it's elevated, and that's only maybe a millimeter across, maybe less than a millimeter. And so we can skim laser beams here, tightly focused to hit the individual atoms. And there's a lot of development behind these types of structures, and they're just, in the last year or two, they're coming online. They're behaving better than the ones that we make from scratch in the laboratory. So this is actually a really big deal, and I think in the next decade, all of these groups will be using such chip traps. Okay, and these are made out of silicon with, in both these cases, there are gold-plated electrodes on the silicon. Okay, so atomic physics. So each atom here will host a qubit, and in the ytterbium ion, if you're wondering why ytterbium, well, there's a handful, only a handful of ions that are appropriate for these reasons. Ytterbium is one of a bunch of ions that have appropriate electronic structure that can store qubits very nicely. And in fact, what we're looking for are atomic clocks. We're looking for atoms that have pairs of levels that are very stable. In this case, the hyperfine ground state in ytterbium-171 has a 12.6 gigahertz splitting. And I listed all those digits. I could list a few more. And the point is we know what that splitting is, and it's very stable. It's relatively insensitive to magnetic fields. This is in hertz. B is in Gauss. In the laboratory, we typically have noise on the order of a milligauss, although that can be made much better. You can do some quick math to show that at a milligauss, we're at, I don't know, a decoherence time of 10 seconds or something. And so in this type of a qubit, in fact, coherence times of 1 second, pretty much you're there from the get-go. That's very easy to do. 1,000-second coherence time has been observed in this precise atomic system, and if we really had to push to hours, we could do it. That's not an issue with these qubits. And again, this is the advantage of having atomic clocks is our qubits. Now, the qubits here, we need to measure them at the end of the day. We need to see which of the qubits are in what I call spin up or spin down, or if you want to call that 1 and 0, that's fine. And in the atomic ions that are useful for quantum computing, we have something called a cycling optical transition, where we jump up to the excited electronic state. This is an optical transition, lots of energy, 10 to the 14 or 10 to the 15 hertz. And we can exploit lasers, narrowband lasers that are tuned to hit a certain resonance. And this is a simplified diagram here, but what happens is if the qubit is in this state, and we have lasers at, in this case, 369 nanometers, there's another 6 digits of wavelength that we have to precisely match every day and so forth. A lot of work goes into that, but that's very mature right now. You can actually buy that stuff. This laser drives a transition, and the single atom will scatter a photon repeatedly because it can't go anywhere else. Well, it can go to these two states, but we also clean up those states with other sidebands on the laser beam. The point is we have sort of an amplifier. I'm not going to say it's not a quantum amplifier. You can't do that. But we're able to take the qubit state and map it onto lots and lots of photons. And even if we don't detect all those photons, and we don't, we only detect part 10 to the 4 of those photons. Sounds pretty awful. We're getting about, I don't know, 100 million photons per second from the ion. 10 to the minus 4 of 100 million is still a big signal. And so even in a tenth of a millisecond, a lot of numbers here, even in 100 microseconds, we get about 10 clicks from an atom in this state. This is a histogram, an observed histogram of doing an experiment a few hundred times. A single atom is prepared in this state a few hundred times, and we see how many clicks do we collect in a certain amount of time. So that's actually a very bright signal there. And the point, of course, is that if we're in the other state, 12 gigahertz away from a 20 megahertz line, the atom's dark. The light goes right through it. It's transparent, and we see pretty much nothing. And the point of this exercise is that these two distributions are so far apart that even in a single shot, we have very high detection efficiency. And in fact, in this particular atomic system, It's been observed to be better than 3 nines. And if we needed to go to 4 or 5 nines, we could do this. We know how to do this. Okay? So we have the buildings of an excellent quantum bit. Lasts forever, large coherence times when left alone, and we can measure it with near perfect efficiency. Well, how do we connect the qubits up? I would say the most interesting interaction that we use lasers for are the ones that will generate the graph, the entanglement graph of the quantum circuit. And these involve, there are a few ways to do this. In our laboratory, we use optical sources. In fact, these are 2 separate optical spectra, two separate beams, if you want to think of that, from lasers. And they're both very far from resonance. This is 33 terahertz. This line is 20 megahertz. So this is a million line notes away. So this is deeply in the dispersive regime where there's no, this light doesn't betray the state of the atom. There's no scattering of photons, spontaneous scattering. But because we have 2 colors here and their beat note is precisely matched to somewhere near this hyperfine splitting, we can drive coherent transitions between the 2 states. This is a very common technique in atomic physics now. It's called stimulated Raman transitions, and we use this here for pretty much all of our gates in coherent interactions. I won't talk much more about that, but you can imagine now a network of a bunch of ions, and we're poking them with laser beams to make these interactions. I'm not going to talk about this. Is sort of, it looks like a table of contents, but I'm not going to cover all these topics here. But I want to tell you a little bit how you entangle ions that are near each other through their Coulomb interaction. And then talk a little bit about a side. This is a little bit of a spin-off of not quantum gates, but actually applying global quantum interactions to large collections of qubits. And it turns out we're doing quantum simulations of magnetism, which is, of course, of great interest to this community, especially as we can scale to larger numbers. But this idea of modularity is really important, and I think we're going to have to think about branching out to a different type of a bus that will allow us to make the system bigger, and talk about that kind of architecture and how it naturally arises in the ion system. Well, let me tell you briefly about Coulomb entangling gates. And so this is a very basic, a high-level slide, but it's actually behind every group in the world that's doing entanglement between ions based on their proximity, the Coulomb interaction. And I would say the first suggestion of this was by Ignacio Serac and Peter Zoller about 20 years ago, who showed that ions are basically interesting qubits and you can actually make entangled states. And the way this proceeds is there are many different flavors, and I'm sort of going to distill a very simple description of them that it's sort of one limiting case, but it has the flavor of all of these techniques. The idea is we have a bunch of ions here, and by the way, they're separated by, atomically, they're miles apart, they're microns apart. And you can, in principle and in practice, our lab and others, we're now focusing individual beams on each ion. So if we want to entangle ions that are even far apart, we're going to, maybe this is obvious to you, we're going to take advantage of the fact that they're connected by springs. The motion is connected. And when you see a picture like this, you really should think of pendulums on springs, and you wiggle one, and you sort of create all kinds of havoc with the others. Well, if we want to entangle these, we're going to apply laser beams of this coherent type I mentioned, that they drive Raman transitions in one way to look at that. But in general, these laser beams will apply a force to the ions. They actually move the ions around. They wiggle them. And I'm going to assume that for this description that the force is transverse to the chain. And importantly, the force depends on the qubit state. And we can, in atomic physics, we can realize this with selection rules and polarization and so forth. So for instance, if the atom is in state spin up, under the influence of this beam, it moves upward. If it's spin down, it moves downward. So, so what we're interested in here are the 4 cases of these 2 qubits, the 4 possibilities. If they're both in the same state, they both move upward together. If they're both down, if they're both up, they move up together, and they're both down, they move down together. And if you consider just the Coulomb energy of those 2 particles, nothing's changed. They're the same. But if they're in different states, up, down, or down, up, then they're sort of tilted on this small triangle. And in fact, their Coulomb interaction is modulated slightly. And if you look at the change in energy in that configuration, it looks like a 1/r cubed interaction. It's a dipole, an effective dipole-dipole interaction. It sort of makes sense because we're sort of by hand making electric dipoles and they're interacting. So when you look at the numbers for reasonable laser powers, these displacements, there are a few nanometers, which again is pretty large compared to the atom itself. The effective dipole moment is huge. It's on the order of, if this means anything, it's 500 to bi. This is more than molecules, Rydberg atoms, and so forth. So we can actually, by hand, make these very large interacting dipoles. So if you want to do a non-trivial quantum gate, you might do this one here, where you take advantage of that energy defect for a certain amount of time. And again, this is a limit where the pulses are really fast. And in this case, delta ET over h bar being pi over 2 is equivalent to a controlled NOT gate. It allows you to make Bell states with local rotations. And the typical time scale for these types of operations, they're not incredibly fast. They're 10 microseconds. If you bought a computer and the clock speed was 100 kilohertz, you would probably be disappointed. Well, that's where we are in trapped ions. But the good news is that these gates can be done with very high quality. Very recent results from Oxford, following Innsbruck behind it, showed at least 3 nines of fidelity on this type of a 2-qubit gate. Single qubit gates, single bit rotations are much better than that. That's, all the labs now are routinely doing many nines. So this is actually, things are looking very good. Now, you should be worried already that this model I showed you only hits those 2 ions, and what about in 10 microseconds? In fact, we're making phonons. It's just a mess hitting all these other ions. And indeed, this data from Oxford was with exactly 2 ions, not 20, not 2 out of 20. So there are big issues here on how you can scale even the ion system up in a small module. So let's look more realistically. If we have a bunch of ions in a line, and I'm not talking about 1 million, I'm not talking about 2, I'm talking about some intermediate number, maybe 20 or 50. Well, if we want to control all these phonons, there are many modes of motion. And in fact, if we, let's see, limiting our discussion to the transverse modes of motion, we find that this, by the way, is a spectrum of normal modes, if you want. So the x-axis is frequency, and this is all classical, a classical Coulomb chain. The low frequency modes along the axis are actually not desirable because they're low. They're very low frequency. By design, if we want to make a line, a linear crystal of ions, we have to weaken one axis. So these modes actually aren't they're very useful for exactly 2 ions, but not for lots. So we concentrate on these transverse modes, which are very high frequency, which means they can be laser cooled much easier and so forth. The problem is the modes are sort of all squeezed together. And this is a problem if you want to isolate a mode. If you want to couple to just one phonon mode as your bus, you're in trouble. And in fact, these forces we apply are off-resonant from these modes, but you can see that if you tune a laser here, you're pretty much going to see all those modes. There is a slight difference between the modes, but you're pretty much going to see them all. And if you do the math on the couplings, you will get this dipole-dipole type coupling if the laser tuning is big. But the problem here, there's a scaling problem. You can see this. If you keep adding modes, they all get packed together. And in fact, the scaling is not so great with the number of ions n, that is the spacing between these modes. So it appears that you're going to need to somehow deal with all the modes. And this is sort of one reason why I don't think anybody wants to put 10,000 ions in a single trap and deal with all those modes. But 50, 50, it's maybe not such a huge number. And I think we have a model now where we can think about dealing with up to 50 or so on the order of 50 ions and deal with even all those modes. Many of them, it turns out, aren't so important. So in the laboratory, we're actually applying gates. We're set up to do 32 ions. At least optically we are. In the trap, for other reasons, we're trapping about up to 10, and we've just been playing with 5. So I could extrapolate down to 1, I guess. But 5 is actually not a bad number to start with because you do have, it's a multi-mode problem. And we can send laser beams. We have a system where we can pretty much couple to any pair of these ions. We should be at 10, look, I knock on wood, we should be at 10 pretty shortly. We're all set up to do this. We can hit all 10 at the same time. And this technology is actually, for those of you that are interested, we have a very interesting laser modulator that has 32 channels that we can turn on and off, individual beams. And these aren't ions. These are actually the individual beams themselves hitting a very cheap camera. The pixels are pretty big here. But we can put a different spectrum on each beam and a different intensity on each beam. This is actually a really powerful tool for us. And so with 5 ions, we've been playing around with this to do, this is a different type of a gate. It's not exactly a controlled NOT gate, but it's a useful gate, and it's the one that we naturally have. We call it a Mulmer-Sorensen XX gate. There's the truth table. I won't talk much about it, but we've used, by trapping a sample of five ions, this is data, I won't get into the details here. It's partial tomography of 1 and 2. We tried to entangle 1 and 2, and we did so. These are the populations, and this is the so-called parity oscillation showing the coherence of the off-diagonal elements. Same experiment, there's 3 and 4, there's 2 and 4, 3 and 5, 2 and 5, and 1 and 5. And so there are, let's see, there are 10 possible gates, pairwise gates you can do here. We can pretty much do them all, and they're all pretty decent fidelity. They're not 3 nines yet. But the important point is there are 5 modes of motion. How do we deal with those? Well, I won't get into the math, but the pulse shapes of these lasers are tuned so that all of the modes of motion get disentangled at the end of the gate. Now, for those of you that are experts, some of you are, you know that this is a little tricky because the physics here is that we have a different dispersive detuning from each mode, and they are not commensurate. So we have to play some tricks with the laser pulse to make sure that all these modes close at the end of the gate. But this is really promising. I don't really see any problem scaling up to a few dozen using this technique. Okay. And again, here's a little bit of a sidelight. I'm not going to talk about all these. I'll talk about one of them. The idea of applying a global beam to hit them all. So we don't think of discrete gates anymore, but in this case, we think of the interaction with a laser beam hitting all the ions as a global, it's actually an Ising type interaction. It's not type, it is an Ising interaction between all pairs. But it's a fully connected graph. And so we can basically apply adiabatic protocols by applying a transverse field to the Ising couplings and measure correlations as they develop. So just as a warm-up, here we have experiments with exactly 10 spins. And here is just a simple measurement of all of them prepared in what we call the bright state, spin up. They're all in the dark state, spin down. Now, in this experiment, we applied an antiferromagnetic Ising coupling. That is a positive sigma x coupling between all pairs. And the coupling falls off with distance as roughly 1 over distance to this power. This is actually a tunable parameter. So it's a long-range interaction. We can, in practice, tune for dipole-dipole coupling. Alpha is 3. The sweet spot in the lab is, say, between 1/2 and 2. So this is actually a knob of the interaction range of this Ising model. And so what I'm going to show is an adiabatic, an attempted adiabatic ramp down of the transverse field after preparing in the ground state of the transverse field. So this is sort of the standard adiabatic protocol to find the ground state of this Ising model. So out of 2,600 runs, and again, we can measure every correlation function you want. We can measure 10-body correlation functions. There are 1024 configurations of 10 spins. We can measure each one of them. Okay? So out of 2,600 runs, indeed, we see lots of the expected ground state in the L ordering, but only 400 and some times. Only about 17% of the time did we make the ground state, the expected ground state. That's okay. It's much better than picking states at random. So we're doing some type of adiabatic protocol here, but what happened to the other 83%? Well, here's where 8% of the other 83% went. It's almost Neal ordered, except we have domain walls that are toward the middle of the chain. These are the first excited states. The next excited states, again, with 10 ions, we know the whole spectrum. It's small enough where we can sort of know where the excited states are. Here we have domain walls moving out, and this is another 4%. Okay, so where did all the others go? Well, let me show you the distribution of all 1024 states in binary order. And this is the initial state. You should think of up plus down to the nth power. So they're all roughly equally populated at about 0.1%. And then these are the two states that we saw in 17% of the time. But we see all this other hair down here. And these are excited states. I showed you a few of them. But there's clearly dynamics going on here. We're not quite adiabatic. And of course, the reason is this is a long-range antiferromagnetic Ising model. It's highly frustrated. The ground state gap is pretty small. And we should have gone slower in our adiabatic ramp. Well, why didn't we go slower? Ions are perfect. We can go 10 hours, right? Well, the Ising coupling is proportional to an optical intensity that runs around in the laboratory. And that limited us to a time of order 5 or 10 milliseconds. So we just couldn't go slower. And this point is made even more clear when we scale the system up to 14, where we have now 16,000 configurations. And that 17% ground state population is now only about 3%. It's because the gap shrunk. and we weren't able to go correspondingly slower. Okay? So you see right away here, there's a problem with this 10 millisecond or 5 millisecond time limit. We can't go much slower than that. And so you might say, well, you have to give up when you get to 50. Well, I would say maybe not, because finding ground states is not the only thing in the world to do. In fact, we've been doing variations of this experiment to study dynamical processes, like directly doing spectroscopy on the excited states. I mean, there are exponentially many of them, so that process itself, you're never going to get them all. But even measuring the low-lying excited states is pretty interesting. We can do fast experiments by quenching the system. Instead of adiabatically turning off the transverse field, turn it off immediately. And we see entanglements actually growing throughout the chain in space-time, following certain curves that in the long-range case lead to very interesting results. Alexei Gorshkov's back there. He's helped us understand the theoretical extension of so-called Lie-Robinson bounds in this type of system. I won't talk at all about this. This is sort of a subject du jour in condensed matter physics, many-body localization. We can now add disordered transverse fields on each ion and have many different samples of that disorder to show the sort of the many-body extension of Anderson localization. Even with a system of 10 spins, we can see certain properties of that. Okay, so this is largely a quantum simulation type project, and with even 10 ions, 10 spins, there's interesting things to do. And we're going to revisit all of these things when we scale up to 50 and so forth. I didn't mention a spin 1. We know how to encode a spin 1 particle in each of these atoms as well. There's some costs expended in the fact that we have magnetic sensitivity that's a little increased, but we know how to deal with that. Well, how are we going to scale this up? Well, it turns out, technically, the reason we're stuck at 10 or 20 is something kind of silly. It has to do with the background vacuum is not good enough. Every half hour or so, a background atom hits one of the ions. And if you have 30 ions, that means every minute, the whole crystal melts. We don't lose the crystal, it just gets very hot. And it takes some time, it takes about a minute to recover from that. Well, we're not taking any data, because by the time we recover, we have another collision. So that limits us to about 20 or 30 right now. We're going cold. This cryogenic trap at 4 Kelvin will have, hopefully, about 10,000 or 100,000 times better pressure. So that half hour will become a year. So as soon as we put this system on the table, and Phil Risherm and Paul Hess are working in our new building right now. Well, Phil's now in Indiana, but Paul is now taking charge of this experiment in the new building on the other side of campus to build this up. And we fully expect to have between 50 and 100 spins in this system pretty soon. All right, well, 50 or 100, not 10,000. Well, again, we're going to need to branch out if we want to make the system bigger. And fortunately, atomic ions are optically active, so we can think of using the photonic degree of freedom to do exactly that. So let's go back to some atomic physics. Here's our qubit, prepared in a definite state down, for instance. We want to map this onto a photon. Well, if we excite that spin down atom to this state with a very fast pulse, much faster than the lifetime up here, we can prepare that state with 95% to 98% fidelity. And even if we didn't make it, it doesn't matter, because the whole thing is going to be probabilistic in the end. But we make that state, and it will eventually decay. It can decay back to where it started, or it can decay to one of these two places. Now, if we observe this photon along the magnetic field that breaks the degeneracy of these states, then we will not see any light, no matter how big the solid angle. That's a little subtle, but it turns out you only have these two channels to worry about. And if you think about it, we now have a post-selected entanglement between the polarization of this photon and the energy levels of the qubit. Now we don't like these states because they're magnetic sensitive. So when we do trigger an event, we immediately shine 3 microwaves on that are very clean, that map the atomic system back to our clock states here. So in the end, given that we have that photon collected along the magnetic field, we can say we have this entangled state. And I hate to even call this entangled because it's post-selected. It only works a small fraction of the time, and in current experiments, well, it's actually not too bad, 0.5%. But the other 99.5%, we have noise, we have garbage. So this is actually, it is entangled, but it's very weakly entangled. It's entangled only in the post-selected sense. Very much like photon down conversion in nonlinear crystals. Not useful by itself. But when we put two of these systems together, it becomes useful. How does this work? Well, we have each ion here entangled with the, say, the polarization of this photon. And when we get lucky twice, now 0.5% squared is really small, I guess. But it happens. It's not zero. When we get lucky twice, these two photons interfere on a beam splitter. And for this audience, I can call this apparatus a very simple boson sampling device, where the two photons undergo something called a Hongou-Mandel interference, or a Shi-Ali interference, I should call it, especially here on this campus, since it was first seen by Professor Ali and his student Shi. Now, when we detect certain correlation events with these detectors here, the photons are gone, but we've basically heralded the entanglement of the spin. So there's an entanglement swapping that goes on here if you want. The problem is the probability of that happening is now p squared. The rate of entanglement then is rp squared, where r is the sort of the trial rate of trying to make the state, which is of order of megahertz. It's pretty fast. And the 1/2 is because we only, half the time we actually didn't get the right correlations, okay? 1/2 rp squared. So again, these are numbers in the laboratory right now. P is given by the detectors have to click. That has some finite efficiency. There are losses. There should be L, but I guess we call it F for some reason. Anyway, okay, so we have losses, and then the amount of light we collect, the solid angle, which is 10%. So this is the 0.5% I mentioned before in the previous slide. You have to square this, and when you put all these numbers together, right now we're at on the order of several per second events we're getting here. Now, only 5 years ago, we were actually at several 10 to the minus 3 per second. So one event every 10 minutes or so. That's painfully slow. We do know how to get to about 10 to the 4 per second when we do better engineering than simply having discrete optics and so forth, and better detectors. I'm glad Bill is here because he'll be happy. I didn't call this hertz. One of his pet peeves is that I've sometimes called this entanglement rate 10 hertz. But it's not synchronous. It's not happening at regular intervals. On the other hand, if you have some time, if you have other qubits around, you can make a first in, first out type of process to make it synchronous. If I can hold on to these things randomly but have a buffer, I can have these coming out at roughly the same rate, and then I could call that hertz. Yeah. Okay. All right. In any case, this is pretty darn slow. You thought 100 kilohertz was slow. This is 10 per second. Very slow. And this is maybe why it's slow. I mean, this is what the laboratory looks like, where we've done almost everything you could do with two separated matter qubits that are entangled. And right now we're getting entanglement at about 10 per second between these two. Here we have two vacuum systems separated by about 1 meter. The magic optics happens behind the black curtain, underneath the black box here. And that's what it looks like. Now, so how is this modular? It's very slow. Well, it's very slow, but I think in the future that photonic connection rate can be made almost as fast as the local connection rate between ions in a single crystal. So now I'm going to start to wrap up here. The big picture is that, well, why do we have to go modular? And I think this next slide is a little provocative. I'm going to discuss qubit economics. How many qubits are you going to have per module? Or let's say you don't even want to think about a modular architecture. How many qubits can we have? Well, I think it's probably true, I can't prove this, that any quantum architecture will run out of steam at some number of qubits. And that number won't be 10 million. It'll be quite a bit smaller. And I think I've given you an idea in trapped ions what that number is. I think it's between 10 and 100. But here I'm going to plot, this is sort of like a supply-demand curve. Let's see, the cost per qubit versus the number of qubits. Kind of an interesting plot to consider. And you can attack me for how I draw this curve, but there is one feature in this curve I know is going to be true, and that is going to take off at some level. It's going to have some threshold. Okay, so here's my fake plot. All right, 2 qubits has some cost, and going to 3 is actually significantly more for lots of reasons. But you know, when you're at 40 or 50, let's say you're at 40 qubits, going to 41. Look, if you've figured out 40, 41 is probably not going to cost much. In fact, this slope might even bend down at some point, per qubit, cost per qubit. Now, classical bits, I mean, costs better go down because you don't have an exponential gain that you can take advantage of. But at some point, I don't know if this is I don't know what this curve is. There's a lot of interesting physics in this curve for each platform. I think in ions it will be somewhere out here, 50 to 100 or something. The cost just grows enormously. Okay, What's interesting about this curve is that, well, again, classically, this would be a non-starter. You cannot scale classically, but of course, quantum is not classical, and the exponential growth of the Hilbert space is what allows us to have a high slope. We better not have too many exponentials, though. Okay. So on this plot, we can also plot constant money. Right? Cost, if you have $1 million, the cost per qubit versus number of qubits is just a hyperbola. And so here they are. And so you can see that if you're going to build a, if you have a budget, 500 million is probably not going to get you more than 100 million. If this is the actual curve of the cost per qubit. So this sort of economical argument shows that you indeed will have to go modular if you want to have a finite budget. And so I think with that, we sort of have this very high level architectural picture that I showed at the beginning, where we have these individual modules that are connected by photons. And if you look at the connectivity graph here, I have some figures from Ken Brown at Georgia Tech, who's thought a lot about this. There's lots of connectivity here. In fact, there could be full connectivity within the module, but it's pretty sparse between modules. So for instance, you might have a graph like this, where you have 4 modules, and this is actually a linear chain of ions, and you can see maybe the ones on the end. There are 4 that are connected optically. These 2 are on the left end, these 2 are on the right end, and they might connect to other modules. And you'll note also that the graph inside doesn't really connect at large distance. There's no connection between this and this. So this is a very interesting graph. It's not just nearest neighbor, it's much richer than that. And it depends on the number, and looking at these graphs is kind of fun to think about what you might consider. This sort of suggests encoding a logical qubit and doing error correction based on these photonic interactions at a distance. Or if you want, you could think of having a switchyard of photonics in the middle here. And actually, a lot of this technology exists, where by the classical configuration of this device, you can interfere any pair of modes that come into the system. Okay? And there's some reconfigurability there as well. I think this will be important to simplify certain applications. So what are we doing in the lab? Well, I hate to say that of this big picture, this is sort of what we're doing in the lab. The simplest thing you could do, well, there's a 1 + 1, which is sort of, that's really trivial, but actually a 2 + 1 is quite a bit harder because you're dealing with both the phonon bus and the photon bus. And there are phase issues that you really have to deal with when you get down to it. These shouldn't have been a surprise to us, but it took some work to synchronously phase those buses so that we can make 3 particle entangled states using both. That's discussed in this paper here, and the phase issues below that. And again, we're based on what makes this possible is we're not at 1 milli per 1,000th per second. We're now at 10 per second. Sorry, Bill. I haven't fixed everything yet. I'm getting there. Okay, so I guess the one thing we like about this system, though, for the first time, we've been able to show that even though it's 10 per second and it's pretty slow, that's still faster than the coherence time of the qubit when left alone. And if you're going to scale this up, you better have these connections happen faster than the spectator ions lose coherence. And in fact, you can show, Robert Rausendorf has collaborated with us on this architecture and showed that if the entanglement time is longer than the decoherence time of the spectator qubits, then there's an overhead that's super exponential in that ratio. So if that number is 10, you have 10 to the 10 overhead, which is a problem. But if it's 0.1, you're in pretty good shape. And in fact, this is data from that same experiment where here we have the vertical axis is sort of success or fidelity versus time here. The blue curve is coherence, I guess the fidelity of a bell pair. And the right axis is the success probability of our protocol. So you can see that we're generating entanglement on the order of several per second, but we're only losing it on the order of 1 per second. So that ratio is actually less than 1, which is a big deal for scaling up. If you look at, for instance, NV and diamond, right now that ratio is about 1,000. So you really can't scale that system up. Now you can't even think about it because the coherence time of the spectator NV centers is so bad. All right, so to wrap up, here's the problem, of course. Even that system, 2 + 1, 3 ions. I mean, here's the infrastructure needed for that. Fortunately, much of this is fixed cost, and I think if we did 20 + 20, the system wouldn't look much bigger, but it's still pretty awful, and I think this scares everybody away. Well, if that scares you away, then this should scare you away from ever developing solid-state transistors, I guess. So I'm certainly of the belief that we lack engineering. This thing can be packaged in a single 19-inch rack that's about as tall as me. We know how to do that, and we're going to do this. This is going to happen in the coming years. Every mirror here has 3 knobs on it. We don't need that. But you know, these are grad students in the lab. This is what we like. We like to have flexibility on absolutely everything. But engineering means making hard choices and getting rid of flexibility for performance. So this all is going to shrink down enormously, and I think we can imagine a system like this going to something. If we can stamp out these modules and make them reliable like an iPhone, I think we'll be able to hook them up. I'm not so worried about paying for it. It's very expensive to do that. But if we can show that you can build one reliably, I think we have a good case to build a really big system. And I don't think we need breakthroughs to do this. Very hard engineering challenges, but nothing, you know, no fundamental breakthroughs required. Okay, so with that, this is my group. Our lab is in the new building on the other side of campus, and this is our funding source. Thank you for your attention.
You have a question. So the modular architecture makes a lot of sense, but I wonder about the switchable interconnects. You could also have static interconnects, maybe a bunch of modules connected in some kind of expander topology. Each one's connected to 3 others. And then you do entanglement swapping using your classical controller. Do you think that the reconfigurable switches would be preferable to this static configuration and then routing via software?
So yeah, the question concerns I guess the switch box in the middle, and I'm imagining this is reconfigurable. In fact, that's a little bit of jargon there. This technology exists. It's called a lambda router. Back 15 years ago, there was great interest in routing optical signals by using MEMS mirrors, and if you had 1,000 input fibers, you wanted 1,000 output fibers. That means there's 500,000 possible connections, and this device was able to link any input to any output with less than 1 dB loss on all of the 500,000 channels. In fact, Jungsang Kim, who's at Duke now, was intimately involved with that project at Bell Labs. And it exists. That technology exists. It's a bunch of MEMS mirrors, and I think of them as sort of old telephone operators that are moving things around. It is reconfigurable. You can do things in parallel, and there's a big gain there in doing that. So, of course, we're not imagining a static graph. My laboratory right now is a static graph, but I think the great news here is that everything to the right of where my hand is exists. I didn't talk about these are inline fiber beam splitters. You buy them. This is a CCD camera with different pixels. You buy it. So that technology exists. Some of it needs to be in the blue or UV, so there's some challenges there, but there are no problems in the long run. Even the MEMS mirrors, we can think about doing this.
Maybe we can take one more question while Aram sets up.
So one of the things that people have complained about in scaling any of the atomic things is so many lasers. And certainly the modular approach deals with that at the modular level. But then, of course, it still is scaling. Now, it's not such a bad scaling. It's linear or something like that, I guess. But anyway, what's your vision for how that's going to sort out?
Good. So lasers is a big deal, and I guess I didn't emphasize that too much. I think of 2 flavors of lasers in this situation. One is the laser that allows you to read out the qubit, fluorescence and so forth, and it allows you to laser cool and so forth. These lasers are, the tricky thing about them is that, you can go ahead and set up. The tricky thing about those lasers is that they have to be tunable, of course, and narrowband and controllable. But fortunately, very little power is needed for these things. And we can now get semiconductor diode lasers that are like smaller than laser pointers, even in the UV. So Mark Kasovich's company, AOSense, we're going to be working with them to develop this. And it's all lockable. They all lock. I think the more difficult laser is the one that does all the gates, the more important one that you have to keep quiet. And unfortunately, for each module right now, I think we're talking about a big frame laser. It's a laser that is used for lithography. It has a key, and that's it. So it's a nice laser from that perspective, but it's still a big frame, and it's not cheap. There's possibly ways to recycle that power. We can think about that, but right now, that's our plan, is to, for every module, you have one of those lasers. And that's sort of maybe 5% of this rack will just be that laser. But you know, you bring up a good point. Linear scaling when each device is $100,000 is not so attractive if you want to have 100 modules. Already you're at 10 million. But it's a good point. And it's one issue with atomic physics is that you have these perfect qubits, but they come at a cost. If you want to hook them up, you have to have pretty exquisite external fields to do that.
Okay, let's thank Chris again.
Hey, this is actually yours, right?
Oh, yeah, that's mine.